we're going to do today is really spend about 30 minutes. I will spend about 25 to 30 minutes. Thushara will spend about that much. We want to spend a bit more time on the discussion. That's where I think we will present some of the material. This talk is based on really my now working in this area for a long time. I probably more than I would say I will count about. I always had the passion for concrete, even when I was studying at Maroto University. That background gave me that very good start. So I had to thank, like, the what I was given in the beginning with in Sri Lanka, and then I went and I could do a lot of things here in Australia, and then to be in other places. So basically, I had a exposure in '96, I think, and to 2001. I was the I was chairing the high performance concrete committee of the American Concrete Institute, international committee. So I had in the committee, the world's best in that committee, and I could be the to chair that committee. So it's a bit of honor there. And so in fact, that one also I could really coordinate a lot of things around the world at that time. And then since they, of course, that been continuing. So I'll give a bit more background. Why I'm saying all this is because it's been a long way. Engineer Nandan also mentioned this high strength concrete and high performance is quite interesting. So there was a time when we said we are engineers, structural engineers, and other engineers. We don't need to know about we don't have to know about the technology or that side. It's totally different. Actually, the all structural engineers had to have a fair knowledge of the technology and design both. And same way, concrete technologies had to relearn the our design side as well. So it's really I use the name materials to structures. We have to have an understanding. We can't go to structural design without knowing the understandings of the material. So it's quite important for us to really have an understanding. So I call it present and future. Just before the lockdown, I attended the in US the ISO sessions, ISO TC 71, which I'm a member of that committees, and that is where the world ISO codes are concrete done. And being a member of the, of course, as mentioned in the introduction, for that, thank you for the kind introduction by Dr. Pradeep. So BD2, which is the main committee, Australia Concrete Code, which really been I'm probably becoming the now the second most senior, but slowly becoming the most senior member in that committee. So I've been involved in number of versions of the code that have given me a lot of exposure. And so this talk I'm doing is overview around the world, where it's moving, and also I gave a talk in the American Concrete Institute as well, the annual sessions. That's again in October 2019, just before the lockdown, and not talking about this particular topic. So it's been really been a lot of development. So I'll just summarize them rather than going through in detail. We are, I think, the present and the future as well. And what we have discussed about our presentations, and Dr. Thushara will be presenting more on the application in Sri Lanka and a bit more deeper into the Sri Lanka scene. So I will be just touching on the overview we are sharing, and it's sharing that presentation bring, and it's sharing that presentation together. So I'll just move on. And so my talk is more of the like we okay, I'll just go to this. So it's an introduction, some applications, the why the sustainability is important. Actually, there are people waiting in the waiting room. So if the host can allow them to enter, I'm also getting this message. Anyway, that's good that we have more than 100 audience. It's really great to have everyone here. So the introduction, so there's some applications, the sustainability, where we are going in the next decade. So I'll just touch on and all that. So this really everyone know about it. The concrete is the most widely used material, the most consumed material, water next to water. So you can imagine, it's not just construction. So concrete industry is becoming so large. I know it's really concrete in Sri Lanka, the most preferred material, versatile material. And we talked about, I've like not been an engineer since steel became popular, then timber, we are talking about sustainable material. However, the concrete is not going to change. We are seeing more and more concrete structures. However, we have to make them sustainable. The sustainability is the goal. And I will just talk about that a bit more. Those who have visited Melbourne, now that's a bit of skyline. This changed a bit as well last so many years, and started a lot of tall buildings as well. And I was quite fortunate to be working in with number of tall buildings in Melbourne, and then a few other experiences as well. My introduction to high strength concrete, the really again as a young, in fact, engineer, I had the opportunity to work with Ken Day, which is he's very close was close to Sri Lanka as well, coming there a few times. I still consider him the best, practically the one who was practicing the best concrete technologies in the world. Unfortunately, he passed away, of course, but Ken Day says a book, if you have a chance, just read that Ready Mix Concrete book from Ken Day. He taught me a lot of things on concrete technology. And so Petronas Tower, really I was not involved in a heavy involvement, but he got me involved with now I work with foundation, concrete mixers. So my introduction to technology came long time back. So it's really, I was very fortunate to be working with him. Up to 80 MPa was used in Petronas Tower, one of the initial introductions. I am known a bit more. I'm very, again, fortunate to be the first in Australia to use high strength concrete in early 90s. And I was recognized in Concrete Institute, that they gave me honorary award in 2017, and it was recognized in Australia. Probably one of the first applications in the world in 90s. I designed this core structure. I was a project engineer for the core, for the most of the building as well. But I used 65 MPa was the strength I used. So one of the first applications, commercial concrete at that time. Now since then, of course, we have moved on a lot. However, this goalposts are always changing, and now we talk about. I will be very brief on these things, but we talk about 150 MPa commercial concrete, and that's where even my team won an award for that, producing that commercial to the 150 MPa concrete, working with Holcim, Australia. So again, that led to another PhD in my group. So so in this case, I want to just mention that in 1950s, maybe I got a slide. Anyway, coming back to all this, then my introduction to Eureka Tower, I was part of the team, although I was in the university as well, but I was part of the Eureka team, and we designed concrete mixers to many other things. Developer was the concrete company, Grocon. So we could really try out a lot of things there. And this is another one of the first to really use commercially. We can do in the lab now. I've produced 200 to 400 MPa in the lab. That's not a problem. But commercially producing is the issue. So that's where I think we have done a lot of work as well. Yeah, uh, can everyone hear me?
Yes,
Yes,
we can hear you.
Yeah.
yes,
No,
Yes.
it was.
I can
I
hear.
think it was sort of muted. Now it's okay. So sorry. Yeah, sure. Now, so thank you. I'll keep going. So Burj Khalifa, really, we are in fact 100 MPa concrete was used. I will share these slides, so you don't need to take down anything. I'll share these slides with the participants. I'll pass it to Dr. Pradeep and Mr. Nandana. And so the 100 MPa microsilica self-compacting concrete was used long time back for this Burj Khalifa. I'll leave the details if you have any questions. We'll discuss later on. I know Thushara also has a couple of slides on the Burj Khalifa. My work was mainly being a part of the team was the designing these columns, very high strength concrete columns, designed for about 80 to 100 MPa sort of, but then actual strength was about 140 when this was measured. I'll briefly touch on those design methods was used there. Shanghai Tower was a key one where second tallest building in the world, 632 meters tall. We had a with Shanghai Construction Corporation. Mr. Dong was my good friend, and this is really a twisted structure, 632 meters. That is the one who was in charge of the whole project from Shanghai Construction Corporation. And this is when so we had a project on pumping concrete together, more of R&D joint project, and that's where that it topped up the 506.9, and I was fortunate to be there. We were looking at the pumping bit more of the concrete to the top, breaking those records there in Shanghai Tower. If there are any questions, I'll mention that. I will not read anything from the slides. We want to save time as well. So anyway, I'll move on very quickly. So the high strength concrete, again, as I said, the goalposts are changing now, but so this definition is a nice definition. Compressive strength more than 50 MPa, high strength concrete, very high strength is 100 MPa, normal strength is less than 50 MPa. So we're talking about even ultra high strength concrete. Thushara also has Dr. Thushara has also some slides on that. Ultra means we could be 150 MPa, 200 MPa. So there's no really rigid definition for ultra high strength concrete, but it's really, let's say, very high strength concrete beyond 100 MPa. Our code we changed to 120 MPa. Now again, that something I led a committee in Australia to change the code in 2000. We went to 65 MPa in 2001. 2009 we changed it to a little bit more 100, and then 120 is in 2018. Now that we are even going beyond that. So I think the Australian code is only one covering the very high strength concrete. American code doesn't have any strength limit to the code. So the same code can be used for all strengths, but that's not been modified for the high strength concrete. ACI 363 committee is the one, even I attended sessions this time in America, but so that's where the high strength concrete committee is there. So we discussed a lot of things in that particular committee. So I can talk about the world scene that way. Let's move on to be very quick. And I'm just thinking, okay. Okay, someone is asking the question. It's okay. This is we had to make use of the, Mr. Balakrishnan is asking the question on what is the minimum compressive strength, high strength, high performance concrete. So in fact, if you stick to, we say high performance concrete, I'm going to say this one later on. High strength concrete is one of the high performance concretes. High performance means it can be different things. So minimum strength is, we can call it like 50 MPa. Good question. There's no fixed number, but let's like about 50 MPa. So the properties don't below that, we just can call it like normal strength concrete. So good question. So just move on. So one WTC, very quickly, because of dual specification they had on the modulus of elasticity and the compressive strength. So this is changing. So the high performance is coming to the drawings. Normally it's in the specifications, but they put it in the drawings that elastic modulus. Sometimes it's not the strength, what we need in a especially tall building, reduced shrinkage, axial shortening, all those things, the higher modulus of elasticity. So not just the strength. So they put it in the drawings itself. Otherwise, so that means to show the importance of the modulus of elasticity. So we are just going away from this, just a concept of strength. We are looking at, I'll skip this definition a bit. I will share that. Anyway, don't forget about the basic knowledge. I'm not going to go through this. Think about the good aggregates, transportation, mixing. That is for the vital for high performance concrete. Don't um, really forget about the basics. Always think about the concrete as a material, cement and water mix, paste. Paste is like a glue, gluing the aggregates together. And then you will understand how to make very good high strength concrete, high performance concrete. Look at the basics. And this is where my first lessons of concrete, so then just remember, cement paste is there, and superplasticized is a ingredient which is really one of the best inventions of the last century in our area construction, the superplasticizers, and that will really help with these pozzolanic admixtures. What are pozzolans? They will add to the equation. I will not go into the, of course, technology equations. We are just briefly covering this. Pozzolans means it will really have the SiO2, silicon dioxide, mixed with the calcium hydroxide, byproduct of the concrete hydration reaction, and make bit more concrete, CSH. So that is, they are the pozzolans. So pozzolanic reaction. So in terms of when you have pozzolans, my advice is always use use the superplasticides as well, because that really will again to really to add to that. Now there's a good questions asked by Mr. Priyant, that is structural engineers. How can we like how can we contribute to sustainable development goals? So yes, very much the sustainability is coming in a big way. I will talk about so sustainability in two ways, because today I'm not, I'll be very briefly touching on, we have to understand that sustainability coming in two ways. And the sustainability comes in the where we are using waste materials, even fly ashes, the slag, silica fumes, waste materials in concrete. Now, because I don't have time to talk about too much, now every concrete now will have, of course, fly ash component in fly ash in Australia, about 20-30% of fly ash. Fly ash adds a durability properties, and fly ash is really essential for underground structures to so on. So fly ash brings lots of advantages. You need to be very careful as structural engineers. The initial strength is, earlier strength is a key. So we can use fly ash, but make sure there are failures. Australia had failures, other countries, especially in the post-tension. These are very relevant to our structural engineers. And the early age strength is a key word. Today, again, I'll be briefly touching on it, but it's really, I won't have time today to talk in detail. But early age, remember, always ask the technologists just not the 28-day strength, but just ask if you're, especially in the post-tension constructions, that ask about what are the early ages, because you want to stress the bars and then release them and all that. Maybe 4-day strength. There were failures, very bad failures, because that early age strength was not achieved, especially with fly ash type of concrete. So we have to understand, we are the engineers, engineers have to understand all that. And that's a good question on sustainable development goals. Other area where I'm heavily working on now is to use many other waste materials in concrete. So the plastics to glass to paper, we are using other materials, even the biomass we call it's like the unwanted materials. We are just throwing into the concrete. And those who attended my talk in February last year, I talked about the waste materials, but I'm happy to answer, doing lots of work on and that area, trying to mix with concrete as well. So answer is sustainable development goals. Of course, we have to really understand that. Now I'm answering questions same time so that it's easy for me to talk. So compressive strength, FCK or FCU. FCK actually this is what's changing the world. The now France Eurocode, as we know, is accepting both cylinders and cubes. Now there are lots of reasons why cylinder is the best measure, but of course we are still in Sri Lanka. We know the cubes. Cubes are fine because we know the conversion factors, everything. But it's more realistic predictions are given by the the cylinder strength. So especially going to high strength concrete, we were one stage in the ACI 363 committee, we were recommending the 100 by 200 cylinders, not even 150 by 300 cylinders, but the smaller size type of cylinders. But now, of course, we allow both. The high performance concrete is obviously very good quality. So the answer is you can use FCK or FCU. Some of these conversion factors are not may not work for low strength concrete. Factors are not going to work. So read some materials, some of these conversion factors, and high performance concrete. So visually getting a bit more even closer the relationship between cylinder and the cube. I'm going through very quickly on those things. Happy to share this bit more, that information. We've done some work in these areas. So I'll move on to the slides. And now I so just also think about cement particles and then silica fume particles are very small. So to make high strength concrete beyond about 80 MPa, good to use silica fume type of material. They are all byproducts, waste products. So it's smaller than the cement. Fly ash is slightly can be bigger, but depends on the properties. Now, this is very quick one where I want to allow Thushara also to talk a bit more, but the ease of placement, compaction, early age strength, long-term strength, permeability, modulus of elasticity, shrinkage, creep. I'll give some examples very quickly on my experience. So to think, high strength concrete is not the only thing. And I was asked to help in the Commonwealth Games pool in Melbourne at that time, the diving board. When it's designed, I helped them to put 65 MPa a long time back. That is just to get the modulus of elasticity so that the vibration is reduced. So for that diving board. So it's not for strength, we use high strength concrete. Another example is that I was, in fact, again, I was asked to help in the Sydney airport. Those who fly there will see a seawall there. The seawall, it is not the strength. Their requirement was to have the 1,000 coulombs, the chloride resistance, durability issue. So it was designed for that rather than a strength. Strength, obviously, high strength concrete gives better properties, but it is not just a strength. So that leads to the statement that here, don't read anything from here, but I'll just say high strength concrete is a high performance concrete. But high performance concrete can be many other things that's in this list. So I will share these applications. I'm not going to talk about all that today. I have named applications of high strength concrete in many, like again, slides here. I'm not going to read all of that. I will share these slides. Many applications we can think about. So that's where the structural engineering comes. The structural engineers are the ones who can understand, and of course other engineers also, extremely important to understand the applications. It can be bridges, it can be especially high strength concrete columns in tall buildings. Remember, it's not just for that. Sometimes we use high strength concrete to reduce the deflections because the elastic modulus increases and the deflection reduces. So as I said, many other applications when you talk about high performance concrete. I will not go into this, but pozzolanic materials are becoming very popular, sustainable materials. And so that I know that even in the green building rating system in Sri Lanka, there's recognition for all that. Now, I had to just mention this metro tunnel. There's a big tunnel happening in Melbourne, big infrastructure projects. All that in the specifications, they say in the metro tunnel, they say 44% of the cement has to be replaced. Now that is where the world is going. So to really, you can't just say just using cement. But of course, the cement companies are all supporting this change with blended cements and many other things now. So that's where it's moving the sustainability side. Super plasticizers, I will not spend time. And for example, like polycarboxylate ethers came in, I would say 15 years back. Could be slightly more, I think, but they are a key for many things. New type of PCs. Again, the superplaza is a very key one. We in the as research side, we do a lot. High strength concrete go very quickly. High strength, stiffness, durability. We can talk about a lot. But more important is the stress strain curve. Stress on the y-axis, strain on the x-axis. Only structural engineers can do this. If you think of the curves, they're parabolic and ductile for low strength. When it comes to high strength, they're very brittle. So what do we do as engineers? So when you're designing the columns, we can put bit more stirrups here, lateral reinforcement, confine the concrete. That will make it bit more ductile. So what I have done in Burj Khalifa and number of other buildings is that made some recommendations to reduce. Since then, it has come to the codes as well now. Like I'm one of the first to come up with these design methods. And okay, okay. The question is, okay, having two cents. Okay, now I like to answer the question straight away rather than waiting. There's a question on RHA is much not practicing concrete rather than okay. RHA, the RISA sash is something I've done a lot of work. I'm happy to even offline talk about it. RISA sash. Only problem in RISA sash, that's why it's not coming to the world. It has to be ground and properly burnt. So it's a bit expensive, the processing. That's why RHA is not coming. Fly ash directly comes out of the as a waste product. So not much processing cost. But rice ash, you need to process them. That's why, although even at that time I did a bit of work for rice growers in Australia as well. But that's why rice ash is not popular. We can start throwing them now to concrete because as waste materials, we don't need to do too much processing. Something we can do a bit more work. There's a paper under my name as well on that, coming from like one of my students from Malaysia. So RHA, good question. Why it's not been used? That is the reason, because it has to be there's a processing cost to grind them or to grind them and properly burn them under controlled conditions. Then actually there's another questions to be considered when constructing common volume of two types of concrete having two strengths. I think that has to be clarified a bit more. Question maybe we'll go to Mr. Garlic can ask that during the question time. How can we for elasticity be calculated DO? Okay, I need to be clarified that as well. Stress strain curve. That's more of mechanics today. And these are offline also. I can be asked from me. I'll like even it's all right to like not share my Melbourne Uni email. You can look at the Google, you'll see the Melbourne Uni email. Please send me some questions as well if you want, even later on. Again, when it comes to RCC, we have to increase strength of concrete as well as reinforcing bar. What is the development of reinforcement? Today, I'll stick to a bit more on the concrete. So I'm happy to answer that offline. Mr. Priyanta, you can even write to me some of those other questions. Today, I'll stick to that because otherwise I'll take hours and hours on this. So anyway, coming back to this, reduce the spacing between stirrups, you will find improve the confinement. That's where I am really like now improving the ductility. Stress on the y-axis, strain. These are the confinement stress. See, when you increase the confinement stress, it becomes really more ductile. So having a 1 MPa, that is where the stirrups spacing can be reduced. Practically, it's about 1 MPa. And I'll show you a reference where you can get a bit more information, how to calculate the confinement stress. Refer to AS3600 Australian code. That's the only code in the world gives a bit more details. Model code, Euro code, model code gives a little bit more details also to find this confinement stress. You can use the confining stress to design now. The design method we have included in the Australian code as well. So if you want to design some high strength concrete columns, look at the 3600. That's the best reference to do that. Now, this is very early stages before all the codes came. Actually, very good question from Mr. Delina asking, does the confinement requirement increase with the higher strength? So the yes, because there is something. Of course, it becomes a bit more brittle, but there are at the moment it's a very good question. Just the concrete strength is not considered to be a parameter for those confinement. It's just based on the so more confinement is needed for higher strengths. But what we do is very crudely say beyond 50 MPa, use this confinement stress at a particular level. So this has, of course, the concrete strength there. So I can talk a bit more on that uh, offline. Also, that's in the concrete 3600 gives a bit more guidance on that. These very early stages, I had this book published in 2001. Since then, Austrian code was developed, which I'm now a key part of that. But these were the Burj Khalifa type of designs came from this work. So anyway, that's still available 2001. I'll leave this. I think Thushara also has a slide of similar, but where the world is moving is just consider y-axis here, particle size as x-axis. So the nano-engineered concrete is here, high strength, high performance here, conventional concrete is here. So where the particle size is higher, specific services area is lower. That's where we are used to the conventional concrete. Where we are moving is high strength, high performance concrete coming in, and to the and then the nano engineered concrete is where now we are moving a bit more. I'll leave that to another time to talk about, and I'll skip some of those slides to really to show why structural engineering is so important, to understand why structural engineering is where we had to be involved with everything. This is some work we did, like now I was also part of it, 96, 97, somewhere there we started this reactive powder concrete, ultra high strength concrete, no aggregates. Aggregate is a weakness. So as engineers, we have to understand where are the weak points. Normally weakness comes around the aggregates, and that's where the weakness is. So that interface, we call the ITZ zone, intertransition zone. This is the work one of my PhD students did work. So this transported to one of the very critical Australian embassies in the world. You may even guess where it is, where the Iran-Iraq war was there. So to Iraq, Baghdad embassy, it was transported at that time to protect the embassy from like the mix that we designed. We used about 180 FPA, no large aggregates, and it protected the embassy there, the top. So it's really a very good application of the early stages, the ultra high strength concrete. No aggregates, so no large coarse aggregates. So we could really do that. Now, nano materials, I'm not talking today, leave it to another day, but nanosilica is the one practically, I think, can be used. That's where, of course, Dr. Thushara can talk about this. PhD was also on nanosilica. Anyway, now this is what you have to think about. We can increase the paste. We can improve the paste to make high performance concrete. Reduce the water cement ratio to levels of 0.2, even a little bit higher than that. You have to use a superplastized to make it workable. But aggregates, that's the work we got an award as well, where 150 MPa we showed the importance of aggregates. High strength concrete breaks through the aggregates. Paste is very strong, but then it breaks through the aggregates. And so because of that, we had to make aggregates strong as well if you want to make very high strength concrete. So just remember that. People are around the world blindly trying to improve just the paste. That's not enough. You need the proper aggregates to really go into that very high strength. So even in Sri Lanka, if you're designing some of these high performance concrete mixers, high strength, high performance, look at the aggregates as well very closely. And sustainable, as a good question was asked, we really need to really get into high performance be sustainable concrete. So of course the UN goals we fit into all that as materials. And also green points we get if you do that. This is one of the key buildings, 6-star rating in Australia. 20% of the oil aggregates were recycled, cement was replaced, steel was recycled. These where the world is moving. So I will not spend time on that too much. So I'll skip that one. Early age, we talked about early age, the importance of that. And I'll just go to the other slides. So pumping is another key one, just touching on that. Remember the pumping. So just one slide I want to show from Burj Khalifa. The what happened was in Burj Khalifa was this was explained in this graph. Pressure on the y-axis, height. When they reached a certain height using 14 millimeter aggregates, pumping pressure was too high, and that was not like they really even picked that up, and then wanted to make some changes at this 300 height. If they had gone in, they won't be able to pump to the top. So what they did was just reduce the aggregate size, sorry, from not from 14, but 20 to 14. That really reduced the pumping pressure. So this pumpability is a key one in the world we will see more and more under high performance concrete. That's from Burj Khalifa. So I'll skip the other type of concrete because Tushar will touch on the fiber reinforce and so on. Lightweight concrete is quite important. Again, you will have these slides, but you can read. But the lightweight concrete, now Tushar is going to talk about. Modular is another area where in the future construction will be done in the factory and then brought into the site. It'll be all prefabricated in 10 years. That's my estimate. And very little work. We need to have some site work, on-site concreting, but lots of things will be done in the factory. So lightweight, because you have to lift them up. So lightweight is a key that you will see more and more. So these are the things as engineers we have to get involved in this process. We can't just leave it to the technologies. I'll skip geopolymer concrete. I'm not going to talk about this today. And actually, I think Mr. Ravi Nisanga could be here, but him and myself, we did a geopolymer trial in Sri Lanka a long time back, like no, maybe 5 years or more than that, maybe 10 years. But anyway, we introduced geopolymer concrete as a trial, but I think it's really pick up a bit more that concrete. I'll skip that. I want to just mention this one. As Bosonic reaction we talked about. Just where the HPC is moving as structural engineers, we had to understand all these investigations, how to make high performance concrete. So we had to understand some testing. Now, at the moment, we are talking about cube testing, workability slump testing, all that. But in the future, we will think about a bit more higher level test. TGA is a very effective test to measure the performance, thermal gravimetric analysis. So TGA will here, and I will not go into detail, but X-ray diffractions to understand a bit more about the material. So that's where we'll see in the future. So if we can do this through microscopes, we can measure. Also, you will see when you use very high strength concrete, there are some thermal cracks as well. So some micro cracks, you need to be conscious about that. I'm just giving only an overview, not details just now, but in questions you can ask. Finally, I'll skip the modeling. Modeling needs to be, that's why we are spending a lot of time. I got a very good couple of students from Sri Lanka, heavily involved in modeling, actually 3 students. And that's where we have a big gap now. In the lab, we may know how to do things, but how to model them, because it's quite important to model everything these days. So that's where multi-scale numerical modeling, we have good computers. I didn't have time, I didn't have those ones when I was studying, but now we got very high performance computers, not concrete. So when I go and talk about HPC, in some audiences, they think it's high performance computers. Sorry, same name. But anyway, computers are quite important. But therefore, we can do some numerical modeling. That's again, if you want any details, I got even PhD students have done this work and continuing that work. So I will skip some of that, the modeling. That's where the sustainability question was asked. Now, circular economy word will come in more and more, where the production and then consumption, that is the demand and consumption, and the waste management. That's where I spend a lot of time also now. And the raw materials. We are running out of raw materials, so we had to use some of these waste materials more. So, and then complete the circular economy. That's a key word you will hear more and more now in the future, next decade. That's where we are doing some work. We're trying to use the municipal waste is a key. We are wasting we are putting to throwing them out, but we want to use them in really valuable products. I call them upcycling. Of course, I covered a bit in that talk last February, but happy to answer questions. We are trying all sort of things put into the concrete. That the concrete is the best place, but we need to understand the durability, all that. Otherwise, problems will come. We can't just throw them in and then think it's all right. So that waste of paper, cardboard, aluminium, plastics, glass, all that we can really, we are doing work trying to put into the to make high performance concrete. For example, if you're using plastics, we think it will improve the tensile strength. So it's like a waste material, but when you throw it in, we think that it will improve the plastic properties of the properties of concrete, and it can absorb more energy. It'll reduce shrinkage cracking and early age cracking as well. So plastics, although waste material, it'll really be very useful. Take paper. We are thinking the cellulose fiber, so it can improve the again that rather than using some other fibers, you can use that paper to really improve the like now reduce that early age cracking, and especially used in concrete roads and all that. So these are waste materials. Tires, we spend lots of tires. Why not? We know how we can use it in with concrete. So that's going to come in the next decade. Is all about lots of waste materials or like no other those materials converted into raw materials. That's where the high performance concrete will be going. So I'm redefining that. I'm sure others probably will think about it the same way like me. Using these waste materials, it is a high performance concrete because we can improve that, and not only that, we are really taking material away from throwing them out to landfill, make it sustainable. So waste glass, I will not touch that. We are doing lots of work trying to put glass in. We are trying to even put in this very important metro tunnel project, some of the temporary structures, glass in concrete. You will hear a lot. I mentioned plastics, glass, even food is a big material. We want to reduce the food waste. So we are trying to see whether anything can be done. No, concrete is the first one which comes to mind to use these waste materials. So you'll hear a lot on that. The glass to waste tires. These are all lots of work we have also done. So any questions that you have later on, I'm happy to. I take a long time, and but before I finish off, now I will finish off just very quick answers to these questions. So now I say, yeah, so Mr. Priyant again asking, the aggregate strength is more important. Sri Lanka aggregates have higher strength, but do you think we use it as engineers to means of sustainable development? Now, yeah, of course, that's a very important one. We are thinking of using some even recycled concrete aggregates now to really improve the sustainability. So it's really we shouldn't be wasting anything. So rather than using raw, of course, we had to really use quarrying. We will run out of quarries and aggregates and all that. We know we are already running out of sand, river sand. So now the manufactured sand, and and then of course the even sea sand trying out, even in Sri Lanka, So those things to make it so high performance, we had to redefine to make it a bit more sustainable. It's very good point, and that we had to consider like high performance as well. So again, Mr. Balakrishnan asking, is it possible to use waste tile or bricks to produce high performance concrete? Like it's a very good point. Construction and demolishing waste is a big problem in the world. So that it's just that there's a small processing issue, and bricks there are issues. Waste tiles can be used, yes, because ceramics, it can be, even ceramic tiles are stronger, so it can be used as aggregates. Yeah, we have done that a little bit on the tiles, but bricks, it be highly unlikely bricks can be crushed and used, because it's a will become a bit of a inert nuisance to the concrete. But it's like no, it can be used. So how can we use these non-biodegradable materials in Sri Lanka? I'll leave it to another talk, Mr. Priyanta. You can contact me, like in the plastics, and it's a very good point. The plastics of yeah. So that's a good question. I can answer that question, Mr. Rohan, asking the question why we can't use plastics for concrete. What will be the limits of using plastics in concrete? Of course, we have to understand more. It's very early stages. We can't just throw plastics. It has to be crushed into pellets, smaller materials to replace aggregates. Even the plastics can be used for replacing aggregates. We are using plastics in other applications as well. So yes, it can be used in concrete, but there could be some limits. Yes, the strength may go down slightly to also things. So we need to understand. We are developing for some waste materials, some accelerated testing methods, because it has to be evidence based. We call it. You can't that you have to show that it's a durability and all that. So we don't know yet. So we can't wait for 10 years. 10 years is where the problems may come in these concretes. So we know if it's close to the sea, it'll come. Even marine environment, in harsh environments come earlier. But so that's why we can't just throw the materials. So we are developing some accelerated methods. So with really to rather than waiting for 10 years. That's where there's a gap as well. The testing. So it's a very quick overview of where we are going. I'm sorry I couldn't give a lot of details, but I'm sure there'll be a lot of questions in the discussion sessions. So I'll just stop there, and I must allow Mr. Thushara to talk, Dr. Thushara to talk as well. So yeah, thank you very much. But I'll be here, of course. We'll answer more questions in the question session. I'll just stop there.
Described by Professor Priyan. So high performance concrete for sustainable construction. So I have organized my slides in a way that, okay, just give introduction, very brief one. Then we will move into high performance concrete. Professor talked a lot about it. Then we will see concrete application in major projects worldwide, and actual application, because I have been in the cement industry for almost 10 years. So let me share some experience. Then we will talk a little bit about sustainable construction and future. I hope, Professor, you can see my screen, right?
Yes, we can see your screen.
Okay. So just to get an initiation, 13% of the world GDP is due to construction related spending. The state of the industry, the future is bright. So everyone knows it. As engineers, we have nothing to worry. So we have enough work to do for years to come. And so this is what you see here is Shanghai in 1990, and in 2019, after almost 30 years, completely different now. So a lot of concrete has been used. So if you just ask a question ourselves, in Sri Lanka, few years back, this was the situation. So even I can remember when we work in cement industry, so we always used to say by my CEO, whatever said and done in this country, cement growth is 6 to 7% annually. So it can be any situation, the cement demand is growing, construction is booming. So this is now a few years back, of course, the port city will be like this in future. So this is where actually we need to apply our knowledge and everything in building this, because sometimes building and the maintenance of these structures will be really cost for us. And some of the countries at the moment, they are experiencing really difficulties in maintaining it. The major issue in the world is most of the work being done around 30%. This is why McKinsey survey, 30% of the work are rework actually. So you have to do 30% of extra work when you do anything in construction. So rework is the major issue. And second, the nearly 50% of the construction companies report is spending 1% or less on technology annually, because construction company doesn't invest much on technology. And as Asian also, sometimes we are spending quite low in our particular field. So this is one other critical area that we need to work on. So I'll skip this. So steel is really good for long span buildings, and concrete, of course, used for high-rise building, road, bridges, harbors, water projects, etc. Why this concrete is so popular? Mainly can achieve very high strength. Means actually you can support heavy loads. Those are very much durable, because it's used to say that concrete getting stronger every day. Actually, if you handle concrete properly, so this can last 100 or 1,000 years sometime based on your design and all others. And structurally very efficient material, which means easier to go high and protect against fire. So it's really good for fire, because compared to some other material, I think even 9/11 attack, after 9/11 attack, many people thought of concrete instead of some other material. And vibration and all others can absorb really well, good for high damp and structures, and resist chemical attack, mean does not rust. Actually, concrete rusting does not rust, but there are some durability concerns to be considered. And it can absorb impact, protects against blast compared to most of the materials. And actually, we can talk on these a lot. We can continue. Can be made into any shape. So customization is quite easy. So because of all these, not all these, there are a lot of others. The concrete is really popular in the world, but as engineers, you should design your concrete to match expected performance. So this is where we have the challenge, because not like most of the other material, most of the other material you get from factories, so with very high quality standards and everything, but you produce concrete mostly at site or in a ready mix plant in very site condition. Then this is where knowledge on high performance concrete, application of high performance concrete will play a great role. So with that introduction, I move into the high performance concrete. Professor talked a lot on this, just as an initiation. So if we ask a question, what is conventional concrete and what is high strength or high performance concrete, or what are the nano engineered concrete? Conventional concrete, we used to have just coarse aggregate, sand, cement, water, maybe a little bit of some other material. But when it's come to high performance concrete, you have fly ash, silica fume, can be some other finely ground minerals, which is not much used in Sri Lanka at the moment, but I think it will be popular. And when it comes to nano level, people started to add nano material into concrete, like nano silica or any other nano material, nano titanium dioxide, like. So when it, because our other topic is sustainability, many people talk about sustainability because of two things. Because cement is a very bulk production that you need a lot amounts in construction. So, and it's, if you take the cement in the world, it's produced 5 to 7% of the man-made CO2 in the world. Second, the amount of material which is available for making concrete or the cement is depleting continuously. So it is going down. So you need some replacement material. But only other time, Other hand, you can enhance your properties by adding all these materials. So these materials, Professor talked about it. So if you simply take that, it can be fly ash, it can be pozzolana, it can be slag, or any other burn shell, any other material, or rice ash, or then it can be next level silica fume, or it can be like nanosilica. So our question is, how much we can add fly ash into our concrete? How much we can add slag into our concrete? How much nanosilica or the microsilica would be? At least we should know by thumb rule how much we can add to concrete and how we can select these materials. So I don't want to discuss much about it, but if you want to have more detail, you can refer to BS 1971 cement standard. It's talk about 27 common types of cement. And in Sri Lanka, we have, of course, 4 types of cement, but only 3 types of cement are produced at the moment and which are used in the industry. So now our question is how we can add this material into cement or concrete, and where we can add and how we can do it. So this is the critical question. So say, okay, fly ash, how you can add it? Whether can you add it into cement? Can you add it into concrete? Likewise. So let's see the very cement production very briefly. So this is cement production. You have raw material and you have to grind it, then you have to preheat it. Then this is the heart of the cement production called kiln. Out of that you get called material called clinker. Then for that, when you add gypsum, you call it OPC. And when you add some other material like fly ash or any other things, in Sri Lanka, you can add up to 35%. It's called PPC, or in Sri Lanka, it's called BHC, blended hydraulic cement. Other type is Portland limestone cement, PLC. You can add limestone 20% into your cement. So whenever buy any cement bag from any place in the country, so you get one of these. Either it's OPC or the PPC or the PLC. But this I have plotted to the ENE standard, but I don't want to talk much about it. So this supplementary cementitious material. So we have a common word for anything we add instead of cement or as a complementary material for cement. We call it supplementary cementitious material, SCM. So what we talk so far, like fly ash, slag, microsilica, all this come into that category. So those are basically should come from, usually come from plenty of local natural materials can be, or it should be a byproduct of any other industry, because sometimes it is not easy for you to manufacture those because sometimes it will not be economical. So most of these coming from byproduct from the other industry. So very good example is Norakchole power plant. So this is Norakchole power plant, and this is coal we are used for the coal power plant. Then during the process, you get 2 types of ashes. One which is coming down or the bottom, it's called bottom ash. One it is fly. What fly is called the fly ash. So these are the basic 2 type of ashes you got from the coal plant. Bottom ash. Bottom ash in Sri Lanka, no one uses at the moment. But fly ash, just really good fly ash we have in Sri Lanka. Those are class F fly ash. There are 2 types of fly ash. I think you are aware of, class C and class F. So if I just show you what photo, this is bottom ash in Noracholi. I took this many years back. We have heap of bottom ash. I think as engineers, it is our time for us to think to use this, because I always used to tell this is a gold mine for us. So we should use as engineers somewhere. Anyway, So my question previously, what I told you is, so now you are aware that we can add many material into either cement or the concrete, can be slag, fly ash, or pozzolana, or it can be limestone. So these materials are divided broadly into three categories. One called latent hydraulic, this is slag. So means actually with the water, you can make them react actually. The second material called pozzolanic material. All these fly ash, natural and artificial pozzolana, rice sauces, all these come into this pozzolanic category. There you need an activator to activate it. Probably you have to use it with the cement. Third type is called inert, the pillar. It's more mainly like limestone, act as a pillar, but there will be very limited reaction only. So these are the three type of material. Then we will see how much we should add, how we should do it, and all others. So the amount of these material can be added into our concrete mainly depend on their chemical parameters and physical parameters. So if you see slag is like aggregate. So when you add it, of course, the workability goes down. You can see this type of material, if you add into your concrete, of course, this can be size same as cement, but when you see from the closer view, it's like aggregate. But the pliers is spherical. So wherever you add pliers, you have very good workability. So wherever you want workability in other sense, you better add pliers. Then pozzolana also like this. So when you add, so probably workability can go down slightly, but not like slag. But all this can be adjusted by the admixtures. We know it, but of course it will be costly. So I skip this. So all this material, as I mentioned, when you add, you should know chemical parameters, you should know their physical parameters. Then you can decide which material up to which level you can add it. So if you want to go into depth, of course, there are a lot of technologies like we do PCR test today. So you can go into the material and see how this material works. So this is very small concrete particle. Then you can gold plate it, put into the SCM. Then you can see how concrete looks like. So this is like a jungle. People who knows this is like X-ray. So everyone cannot understand. Of course, expert can understand what is each material and how its work and all others. So as I previously mentioned, fly ash is very much spherical in in shape. Wherever you add, the overall system workability will goes up. So this I skip. So this shows that even though we say whatever said and done, for particular application, you have to use this material together and you have to see actual, you have to do trial mix at lab, probably at site, then you have to use at your particular application. So with that knowledge, because professor also talked a lot about it, so I will move into the concrete application in major project. I spend a little more time here because this is where we have to apply our material in concrete. So this is quite interesting example. This is Burj Dubai or the Burj Khalifa. And you can see the environment is really aggressive. Or it's like, it's always used to say it's the World Concrete Lab. So here, let's see how they have used this material nicely. How they have used it. So this type of building, Lotus Tower for us, Mr. Shiromal is here, so he has very good experience on it. So we need to pump concrete. So no point of making very good concrete at the bottom, but you have to pump 300 meters in Sri Lanka and Burj Dubai, I think more than 500, 700 meters. You have to pump it. So second, you have to take care of the heat of hydration. So how you manage heat of hydration is mass pouring, especially it can be pile cap area, can be even bigger retaining walls, all others. So heat of hydration need to be managed. Then in the main columns and all other strength matters. So how do you select your material to match all these? Is our using our knowledge in engineering. So Lotus Tower, so I can remember they have used 25% fly ash blended cement for most of the applications in general because of it's really good for heat of hydration. You can get the required strength, and it is really good for pumpability. On the other hand, when you see the Burj Dubai, this is just one example of using this material. So I'll just go into it. So in thumb rule, it says that if you want durability, you have to use around 25 to 30% of fossil-link material. I think Professor will share more. Like fly ash, pozzolana, it's good to have 25% of total cementitious material. I should tell, because total cementitious material mean in this example they have used fly ash and microsilica. So you can see, so this particular mix design is used for the column C80 concrete for the level 100 to 126. They have used fly ash 18%, microsilica 9%. So 18 plus 9 mean 25%. So as I mentioned, at least 20 to 25% is required of these material for you to have a durable structure. But why they have used fly ash for these column is because pumpability is really matters. So very interesting thing is in Sri Lanka, probably you use cement, 400 gram of cement for grade 40, 45 concrete. But here for grade 80 concrete, they have used only 400 of cement and sand, something like this, because these are self-compacting. Amount of sand, amount of aggregate is almost same. And as Professor mentioned, so when you go for higher strength, better to reduce the size of aggregate, because aggregate weakness become very critical in high strength. So they have used 10 millimeter aggregate. Of course, very high amount of admixtures. This is quite high. In Sri Lanka, usually it's around 1%. And water binder ratio is 0.3. So this is where actually we need to move. We need to use it, these high performance concrete design. So I will give you some other example of the same building. So with that, so if I just ask a question from you, for the pile foundation, actually what do you recommend? Ordinary Portland cement, fly ash cement, or at the moment we don't have slag cement. If you have slag cement, fly ash, pozzolana, I'll take as one, fly ash cement or pozzolana. So as I mentioned, it depends highly on your requirement. But when you consider durability, better always use at least 20-25% of pozzolanic material in it. So for the pile in this particular project, Burj Khalifa, so they have used 23% of fly ash plus 7% of microsilica, mean total 30% of pozzolanic or the 30% of cementitious material, except cement, replacement has been used for piles. So even you can use slag, this is up to you. But if you replace this with slag, usually it's used to say that you have to use the double the amount of fly ash or the double the amount of pozzolanic material or the fly ash when you use slag. So you will see the next example, pile cap or the retaining wall. So in the retaining wall, it's a very big structure. Workability is not a critical issue because it's quite huge structures. Then you have a choice to go into either fly ash or the slag. But when you consider these durability concerns, probably fly ash both these good properties. Second, these are huge structures. Then heat of hydration matters. In that case, you better, if you have option, go into slag-based cement, which you can go more replacement of cement, and it will give a very slow heat gain, of course, very slow strength gain. In that case, you have very slow heat gain. So probably, I don't know, probably some of you are aware, if you are, this is the first time that you are aware of this type of mix, 57% of slag, 7% of microsilica, mean 64% of cement replacement with some other material. I'm sure most of you like ordinary Portland cement. So here we are replacing ordinary Portland cement, 57 with slag and 7% with microsilica. So whether this is good or bad, actually, the Burj Khalifa, they should have used ordinary Portland cement easily for this structure. They have enough money. Of course, they have invested a hell of money. But this is, they have used 57 of slag because really good for high performances. So if I remind you once again, so I'll show you the complete mix design later. Then, okay, we start from the pile. It's around 23% fly ash, 7% microsilica. Then we went to the pile cap. Then it was 57 slag, 7% microsilica. Now we have walls. Here we need more strength. This is the difference actually. Now you have to differentiate what you want, because for the pile you don't want that much strength. For the pile cap you don't want that much strength, but the column you need probably you need the highest strength for your building. So it's here, then you should not go fly ash into very high level like 25% or 35%. It's better be in 15, 18 level, then 9% microsilica. You have add more microsilica to get moisture. So likewise, if you see overall all mixed design of Burj Khalifa, this is part of the information. So one thing you can see is cement, amount of cementitious material, not only cement, total cementitious material, they have maintained at 550. They didn't go beyond that because of durability. Then fly ash, 12 to 24%. Then microsilica, 5 to 9%. They have used it. And slag, 57%. I think this is a very good thing. As engineers, we should get into our mind. So these are the ranges that we can move on. So I move quickly. So this is a complete mix design. You can get it even from the Google. You can take it how these mixers can be taken from the Google. So I move quickly. In Sri Lanka, mostly pile caps are doing at around grade 40 concrete. Columns will be grade 70 like. So very similar application can be done. I move quite fast because I need to go quickly. So here I stop for a while. So Lotus Tower Foundation. So we involve, actually the professionals are here, Professor Priyan, Mr. Shiromal, all involved in this structure. This is where you need to be really worried about heat of hydration of the main foundation area. So large concreting or the mass pouring, when you talk about it, mainly we have to consider two things. One, maximum temperature of the concrete should not go beyond, say, 70, 75. And temperature gradient should be in the level of 20 to 25. Otherwise, there will be a lot of issues. Temperature gradients high, there will be some surface crack. If the overall temperature goes higher, there will be some long-term durability issues, which can be very costly for us to repair. So how you can cool down the material is quite easy. Probably you have to, the best way is to reduce the temperature of any concrete to shade your aggregate. Or like nitrogen cooling is not available in Sri Lanka as far as I know, so can be used for, but it will be very costly. So this is foundation of Lotus Tower. So we have talked about it. So concrete also very much similar to all other industries, like your industry structural, you can model them. Then you can model. This is actual model that we have done for Access Tower 2, which is in operation at the moment. So you can see, you can model your structure and see how it's work. The red line shows the model, then the black dotted shows actual figures. So probably when you have mass boring, you have to do these together. So as we were discussing about high performance fly ash, microsilica and all others, this is how you can bring your curve, the temperature curve, brought down with pozzolanic material. So as an example, the green line is 100% OPC. If you use it, your temperature will be, this is just a trial which is done for mortar, but it will be like this. When you add fly ash into it, it drastically goes down. So say 30% fly ash, the temperature will go down drastically. If you add, because if you want strength again, you have to add microsilica. If you add microsilica, this moves other way around as well, but still the compared to OPC is quite good. So I'll move quickly because we can discuss any question later. So this type of material, this is Colombo Southport. They have used blended cement for this. And this is Hambantota Harbor. They have used not only blended cement, but as far as I know, they have used 100% sea sand for this structure. And in a particular structure, concrete, high performance concrete will be different level, different performance can show. As an example, in a dam, very low strength you use for the dam body because you need just the weight of this. So you need very quite low strength. But like in a spillway area, you need very high strength concrete. So here we should be very careful when you select cement or any other material. They should not give high strength actually, especially high early strength. Then you can use manufactured sand for applications. So this is where you have more challenge. So you are not asked to use blended cement, but you are asked to use blended cement with some other new material like manufactured sand. It can be sea sand. Always you have to perform particular mixes. So this is Colombo City Center. You can see because this is your area, of course, you know very well. So this is the only reinforcement that you use for your structure and how it looks like. But when you are really good in this all concrete or the structural, I think it will not be enough because then people ask you to rotate your building, twist your building. Some architects, I say, okay, probably want this type of building in the future. So as engineers, it will be really hard for us to manage all this. So this is a classic example, Altair. Already we have the slant building. So not only the compressive strength, but other like flexural and modulus of elasticity, all others plays a critical role. So it can be precast, or it can be roller compacted concrete. It can be shotcrete, again precast. So you have a lot of things to play. So with that, so I'll come to the last part because we need to have discussion. Sustainability of this industry can be done in many different ways. People are talking about low carbon cement. It can be low carbon concrete. What you can do is mainly what you have to do is you have to have the resource efficiency, alternative fuel, alternative raw material should be used, or the novel cement. Energy efficiency should be maintained. So carbon reuse, people are talking about, can you use this carbon dioxide back in concrete? Because when you do something, even again, you can make calcium carbonate. So low carbon concrete, likewise, as structural engineers, you can design it properly. You can use smart material in it likewise. So this is classic example in Singapore. They have used 20% recycled aggregate to to get green label for this particular structure. So precast will be the future. So I think everyone will move into it. So what you see here is a precast site, which is very much similar to our site at normal place. So this is quite new. Prefabricated pre-finished volumetric construction. I think we don't have it now in Sri Lanka, but in Singapore it is very popular. So this is actual site I have visited a few years back. So there you bring complete room, including finishing, fitting, everything. You put it there. This is like Lego. You put it there, do some small concreting and all other, and you fix it. So this look like this. So complete building. One element, bring it there, put it there, and use it. So we can talk continuously for, I think, many hours. Lightweight concrete, pervious concrete will become very popular. And because nowadays, actually, I used to say our concrete structures are really ugly. But many other countries has moved into very versatile structures with fiber reinforcement applications. You can make this type of things with concrete. And ultra high performance concrete plays a great role. Main difference between high performance and ultra high performance is UHPC, maximum size of aggregate that you use is 2 millimeter. So this is like toothpaste actually. So you make it with fiber, of course, but you can achieve 200 MPa, 150 MPa easily. So these are actually structures in the world which is used, can be used for architectural element and structural element. So similar things. And nanotechnology has come into the industry. With nanotechnology, probably these are actual structures. You can build some structure which no need to be either paint or either clean. So these are self-clean structures which has been done in the world. And people are always evolving. So now people want to make not only the nano structures, but sometimes transparent concrete. So with that, I stop. So let's go to a discussion. Professor, Mr. Siromal. So let's go to a discussion. Professor, Mr. Siromal, and all others. So thank you very much once again.
Thank you, Thushara. So basically now I will handle the discussion time. I think both Prof. Mendis and Dr. Thushara gave a very good insight with respect to Prof. Mendis's presentation. He talked about the past and the present and also the future trends in concrete. And Dr. Thushara gave a good overview of the total application side. So it's up to you to now, Professor Mendis is the top, I would say, he's number one scientist in the world on concrete. He has been ranked as the 40th top scientist in the world. So we have a very eminent personality. And Dr. Thushara also has been in the cement industry and concrete industry for a long time with the top cement suppliers. And now he's a senior lecturer at Open University. So it's a time for you to get the maximum out of this session. Let me go through the chat and see the questions.
Mr. Sharmal, very sorry to interrupt, but I have answered some questions as well.
Yes, Professor.
And giving answers, yes, sure.
We'll start from the last. You have already answered the question.
Yeah, I just because just to save time, I answered the number of questions. But
so Engineer Priyan asking, can we satisfied on the sustainable development goals in Sri Lanka? Probably it's like a philosophical question. I think you are the best person to answer.
Maybe I'll just, Mr. Priyantha has asked a number of questions on sustainability. So I tried to answer a little bit in the chat side, but thank you, Mr. Omar, for very kind introduction that you have about both of us, myself and Dr. Tushar. And thank you very much for coming from you like that. So in terms of sustainability, it's something that we can't really avoid, and that's a key uh, term for anyone designing a structure to be sustainable. Now, sustainability come in a number of ways. The word sustainability has a very broad definition as well. Now, I know even we can start with a really that's why the green building movement was started. But it's really to have those the green buildings are sustainable buildings. Now, in terms of when it comes to the material, it's a very key component. So this is the change done. I remember it's sort of came in 80s to start to the world, the fly ashes and so on. I had to really, of course, we had to give a lot of thanks to Dr. Malhotra from CanMet, and like he's the one who pioneered the use of fly ash, and then it came to the world. So in terms of the waste materials, the beauty of that is now fly ash brings lots of positive qualities. They are not just a waste material. So with like durability and Dr. Tushar mentioned about the workability improvement, all that, not just so there are many other advantages of fly ash. So it's not so that using a waste material, if you can improve the properties, so-called upcycling, the word we're using, we have gone beyond recycling now. Upcycling, that is to use the positive properties, that would be really, really good to use that. So that's the sustainable type of concrete. Now, there was a question came up in the chat side. I said I will answer when in verbally. Quantification, that's quite good question. So we will see this life cycle type of analysis being done, quantification more and more. Sometimes difficult to quantify, but today I won't be able to answer everything. Embodied energies, and you can read about that to make it a bit more sustainable. Other sustainable one, so waste materials is a key. Now we were just only used to fly ashes, slag and silica fumes and so on as waste materials. Now in a big way it's coming the other waste materials, like the what we throw out, like in when we obviously the plastics to the glass to paper even, or that if we can use that as an advantage in concrete, then I think that's become sustainable. One last one very quickly is the number of years, the durability. We were designing structures only for 50 years before, and now that we are trained to design at least for 100 years. Japan going too far, they're talking about 300 years. Why 300 anyway? But it's too much sometimes because it becomes expensive. But so usually that's also linked to the sustainability, the durability, where we are going just beyond designing structures for 50 MPa to make it 100 MPa. Third one is that again, Dr. Shah also mentioned this, with the modular precast. That's where I have spent a lot of time as well. That is to bring from a factory prefabricated, bring it and put it on site. When you don't want it, you can dismantle it, remove it, and then so that way you're making it sustainable with this modular type of prefabricated construction as well. So that all adds up to this whole sustainable construction concept, which is really going to be the key in the future. Very good question, sir.
Next question is, let me ask from, put to Dr. Tushara. The question is from Engineer Rohit. He's asking, do you recommend porcelain material for sewage treatment plant? Explain this, considering any reaction that can happen with sewer at later stages. Put special attention on fly ash, which is used commonly in Sri Lanka. Dr. Thushara?
Yeah, Mr. Siroma. So I think very good question. So here, when you add any type of material into our structure, what we have to think is what are the available options that you have, and what is the best. So here we have to in Sri Lanka we have to compare with ordinary Portland cement with what you are telling is like fly ash or the pozzolanic material. So when you add pozzolanic material, can be fly ash or the pozzolana. Of course, reaction can be different, but those will give additional uh, durability for your structure. So probably we can check it. It can be chloride, can be sulfate attack, or permeability, water permeability, or air permeability. So durability wise, fly ash blended, because you asked to specially stress on fly ash blended cement or fly ash blended concrete will give, of course, better performance, because you have to compare with OPC, what's available in Sri Lanka. So fly ash blended cement will be the best option for this. I think Professor Priyan can add on
Yeah,
it.
no, I think that's very, you really, thank you, Dr. Tushar. You really answered very well. And at the same time, I think so it's the, which, the bit of work, like just to add to what you said, bit of work been down now on the high volume fly ash. I didn't talk about that too much. That is a future. I didn't have time to talk about that much, but high volume fly ash, we are also doing some work. We'll see a lot more. We are now replacing up to about 80% of fly ash. So been used, and that one to get the early age trends and all that. So we can use a bit of microsilica, nanosilica, and then we are using some lime there, the hydrated lime. Then we also are using what's called some waste material, the formates, so calcium formates. So to really, so that you can replace, put bit more fly ash. So that'll make it even more durable. And so yeah, just to add to that, yeah, sure.
There's another question, Professor. Like the bigger structures are they are with huge investments. Then can we tell 300 lifetime is too much? Some of our ancient temples are still available in our country.
That's a
But
very good, very good question. Because even in presentations here, sometimes I used some of those temples structures. Even my modular presentations, I start with Lower Mahapaya, where we had the pillars still standing, and so it's true. But it's a good point. I also had some interest. Now, if you think of geopolymer concretes and all that in ancient even the Greek structures, they have used some of that lime and hydrated limes, just some of the to really some binders, or that they knew that at that time. So it is true that they stood up so well. Now the thing is the 300-year only problem is that when you design for 300 years and so on, is really you need to improve increase the design parameters as well. So for example, like where I talk about not just the concretes and so on, just the durability. Yes, we had to really talk about the durability of 300 years. Then we had to increase the cover values, all that. It's true the some ancient structures are standing, but it's really, but still we can't just say because they're standing, we can use it. But the when it's 300 years, we need to increase the design values as well. Like for example, the wind speed we had to increase as structural engineers. Then we had to look at all that, even the earthquake and all that to for higher levels when you're designing for 300 years. Now that way we are had to really spend more money on the structure. That is why I mentioned that we can't go too like overboard as well. No, sorry, too much to use, and we can't just use the normal cover values. They're just designed for. Actually, in fact, we are only now designing on for 50 years in the codes. So we can't just use the code values. You need to do like other calculations to improve the design lifetime, what we call it. For bridges, we are using 100 years anyway now, but for buildings, we still about 50 years. So that's a good question. Ancient structures are standing, but we can't just use because of that, we can't just say, so we need to really improve other parameters. I hope I answered that question.
Thank you, Professor. So the next question I would like to put to Dr. Thushara, that is, fly ash may contain heavy metals. Is there any possibility of mixing them with water when used in the water retaining structures? This was posed by engineer Sampath.
Yeah, Engineer Sampath, actually, this has been the discussion for actually quite long time when fly ash has been introduced in Sri Lanka. Um, but usually when you consider two structures, uh, as I previously mentioned, so now we are comparing with ordinary Portland cement and fly ash blended cement. These fly ash blended cement structures are more dense and really good for durability, and permeability will be very low, air or any other water permeability. So the leaching of this heavy material, so I think we have done some studies with water board, but not in extensive. Professor Priyan can add something. But as far as what we have done in the initial level, so mixing of heavy metal into water is quite low, because these most of the heavy metal or any other material which is in fly ash will be bonded in the concrete, within the concrete. Anything in the surface or at the very limited depth can be mixed into water. But as far as I know, as far as I believe, the level of dangerous mixing into water is quite low.
What about this? Like, say, for instance,
Professor
losing,
Priyan, I think probably he can add his
Professor?
Yeah, no,
experience.
no, actually, I think that's a thank you. I think that's a very good answer you gave. We have not seen, which we call it the leaching of metals into water. We haven't seen that because the mix is really embedded. Even those heavy metals are not exposed. It's a little bit of really it's there, but but however that we don't see that is trapped, and and it's not, we don't see the leaching with mixing with water. I think just want to confirm what you said, Dr. Char.
There are like a few questions I will pose where there's a lot of questions coming up. I will like summarize things like Professor. The one question is about river sand sustainability point view, and other one is from Engineer Galage. Um, bit difficult to read that question. Dr. Pradeep is asking, are there any alternative instead of silica fume which can be used for high performance concrete?
I think it's very good questions. Of course, the river sand we know will be again. Dr. Charo can also add, but the river sand is like we everywhere, not just Sri Lanka. We are running out of river sand, and it's lots of concrete construction, and so it's already so because of that. Luckily, we had the manufacturers sand coming in a big way, and also and even the sea sand, we know we can really now use sea sand. Only problem with sea sand is it's the mental issue, right? People don't want to just use because they think the sea sand is not good, but like no, sea sand has to be used. Washed sea sand sometimes get washed automatically, like now if you exposed it gets washed as well. So that it is going to come. Other one that we are more and more will be looking at is the using glass in concrete. So glass as aggregates, even plastics as aggregates. Now, if you think of glass can be no problem. We don't even see a bit of a strength drop. Only thing is when you're using glass, there's a alkali silica reaction ASR because of the reactivity. So the solution is to use bit more fly ash. Fly ash will solve that problem of ASR. So that's why the waste material fly ash is so good. It's even help in the solving the ASR. So if you're using glass, you need to use bit more fly ash. So that way, yes, there's a still used river sand, but it is we can't really use like that. We need to change that to this other type of aggregates being used. Other question, Mr. Shumal, you mentioned, Dr. Pradeep's
Is
question is very
that is with respect to the
silica
use of
fumes alternatives.
alternative to silica
All
fume.
right, yeah. So I will actually again, Dr. Thushara can add to this as well. The again the like now we went to nano silica a lot at that time, assuming maybe very good to get a comment from Dr. Sharas because his PhD was based on that area, nanosilica. Now, the nanosilica, by also experiences, has not performed the way we wanted to really change. That could be a bit more expensive than silica fume. Now, silica fume is very highly reactive, smaller than cement, so we can really. That's why we are to make some very high strength concrete. Silica fume as to be the a very important ingredient in the cement paste. However, beyond we know that just as I mentioned, cement paste is not only enough when it comes to very high strength. You need to check the aggregates. So at the moment, it's a very good question. Other than the nanosilicas and some other nanomaterials, we don't see too much of like a cheap alternative. There are other ways of we can really use that. Now to make high strength, there's another way that we, as we both of us pointed out in the presentations, the reactive powder concrete or the ultra high strength concrete, take out the large aggregates and just leave the sand, and that really will really like now take out those aggregates, so it will improve. So if you're doing that, you don't need much silica fume. Also, if you want to get higher strengths, you can use some pressure and the high temperature curing. Put it on high temperature, so that will also improve the strength. Then you can get rid of silica fume. But silica fume is a very cheap way of producing that, giving that strength. Hope I answered that question.
Thank you, Professor. The next one question from Galage. It's a comment actually. It's giving a proper maintenance method can increase the lifetime of structures. So there's another. I would like to pose this question to Dr. Tushar. What design guidelines
Somali
Sri
still
Lanka
gives
can be? Dr. Tushar, can you hear me?
no, actually, if you just okay, 1 second.
Yes.
When we add in the to answer the previous question, actually, when we add in different material into concrete, actually, we actually probably not now, but later when you do it, so you have to think of the cost of the material as well, because the cement 1 kg is around 20 rupees, sand aggregate maybe 3 4 rupees, then microsilica 150 rupees, and nano silica probably I don't know 2,000 5,000 rupees. Then performance against your cost. I always used to say that in private sector ROI, return on investment, the total cost of ownership also need to be considered. So that's why a lot of other materials are not very popular in Sri Lanka.
Thank you, Dr. Shara. This question also for you. What design guidelines Sri Lanka can best follow for HPC design, standard EC2 or FIB model code or different guidelines?
Yeah, usually for the concrete, so in Sri Lanka, we used to follow EN code. EN 206 is the main code which guide the concrete. There's another complementary code which is for British. It's the complementary to the 206. it is BS 8500. So one of these cores, of course, is used in Sri Lanka. So, but based on the different material, say fly ash or the say cement, slag, there are some other standard European standard for particular material as well. As an example, for cement, you have to use BSEN 1971. So for testing 196, right? So there are several, of course, European standard we mostly use here.
Thank you, Doctor. So the next question is to Professor. That is, simply explain from Fazil, the engineer Fazil, simply explain about TGA test
Yeah.
methods.
So I think very good question. As I said, that's where we are moving in the future to really uh, like future this test. We are not just relying on the, as I said, just slump test and the compression strength. So a bit of microstructure testing will be done to really look at the bit more carefully for routinely. We do it in the lab now, but so TGA test is more a very good question to simply, if I simply explain, TGA is a temperature gravimetric test, as I mentioned. Now that is the like temperatures increased and the reduction in the material weight is measured. So this is in a complicated way. It's been done automatically in the TGA machine, but that's simply that is what it's doing. Under increased temperature, what is the material loss? So from that, you can identify different materials, which we already know the different materials. So of the perform the how they behave. So from that we can identify the different components. Other two also could come the what is called you can read about XRDs and I won't have time to explain all that. And the SCM test electronic the microscopic testing also valuable.
Thank you, Professor. I think we have already reached 7. I think they are, you may be like 12 o'clock, right?
12:40, 40 past 12.
Okay, okay. So let's as the oh, some more questions. As the last question, I would like to ask one question from Professor. So I can remember Kende coming here and giving 2 lectures. I was fortunate to be there, and at that time, he was talking about that we should be able to make concrete with any material. What is your final thoughts on that, Professor?
Yeah, I think that's a very, he's my mentor in concrete technology, whatever. So it's really, I was so fortunate to work with him. Practically, as I just mentioned, he's the best in the world. We had very good, we are losing a lot of concrete technologies, but I'll be very brief on some names. Meta, we are losing it since to now. So we are losing a lot of, we lost a lot of people, but the, yes, again, the very, Ken Day was the, so in fact, what he went away from what we are talking today is that not just using a code to do things and recipes. So what we're now doing is that to say that we are, so what he, with this, his, the CONAD system, what he did was using the previous properties and what we know and to use the mixed designs based on that. So what we are doing now in this machine learning, we didn't have the word machine learning his time, but what we are doing now, training systems, all that is through that sort of system now. So that is something I didn't have time to mention. So even in the mixed design, we are doing some work on that using machine learning and that artificial intelligence methods to really, so I actually thank you, Mr. Omal, for asking that question, mentioning Kende, because what he did with Conrad system and his book, which is very famous still, he's more famous in US than in Australia, but it's that book. So that's what he did. So so it's really learning from all that, and I think so that's my thought. And actually, I see a message from Professor Ranjit as well. Thank you, Professor Ranjit, also to be joining us here.
Yeah.
Thank you very much, Professor. And also, I would like to have a final thoughts from Dr. Thushara with respect to the Sri Lankan context with respect to cement use and also the concrete technology. I think you have been there for many years, more than 20 years in the industry now. What do you think from like in this industry, what's happening here? I mean, from the day you started and now, the how adaptive the
Yeah,
new
Mr. Kamal,
technologies with respect
I hope
to.
you can hear.
Hello.
Yeah, I can hear you. Yeah. Tell me.
So how adaptive our industry to the new technologies and how it is progressing. Can you give your final thoughts there?
Yeah, Mr. Shiromal, actually, yeah, it's, I think, a very good question. I think very good, I think, question that I can be answered because when I joined my previous company, main cement supplier in 2008, many people wanted OPC, original Portland cement. But the on the other hand, as a company, as a multinational company, we wanted to promote blended cement. Of course, due to it's a win-win actually for the industry. It's wanted many world in the world it has been used, but in Sri Lanka it was so hard to promote this. So as an example, I can say that when you started to promote fly ash blended cement, sometimes even the competitors, even the engineers used to tell that me Gallanguru alu cement වලට දාලා බාල කරලා විකුණනවා. I'm sorry. So people used to tell that. So this is diluting the cement. So this is the way. So, but I think, of course, company get better return in blended cement. I think all companies. But on the other hand, industry also get better benefit. So I think compared to, because I have been in Sri Lanka from 2008 till now, so last 12 years. So very 3-4 years, it was very slow to move, very slow to pick up. Of course, there was some other material that can have some arguments. But nowadays, I'm very happy to see that. So I think we are on par with most of the countries, at least in major projects. Major projects widely, probably because of your involvement, Mr. Chiromal and Mr. Nandana and Professor Priyan, Professor Nanakara, and Professor Ranjit, all others. Because of your involvement, now I'd say the concrete industry in Sri Lanka is going really well. Even we have best admixtures in Sri Lanka. We have best admixture players. So I feel we are on par with most of the countries. Of course, there's a lap between very developed countries like Singapore. But I think comparatively, we have made very good progress in last few years. Thank you.
Thank you very much, both of you, for giving wonderful
Mr.
lectures.
Siromal?
Yes.
Actually, one more thing that I am really happy that Professor Priyan is one of my supervisors in my PhD.
Thank you for that very kind comment. And Professor Ranjit here as well, I think. I'm sure.
Yes. Okay. So thank you very much for both of you for having a fruitful discussion and also very wonderful lectures that you have given us. So it was a very meaningful 2 hours. Thank you, Professor, for joining from Australia, and thank you, Dr. Thushara. And we are very grateful from the as the executive committee for joining this session, and also Dr. Pradeep for organizing all this, and also the Hasti Cement for sponsoring. And also, I would like to thank all the participants being here with us. I think there are maximum number that could enter the session was 100, and it was limited. So we will next time we will correct. We will make sure that everybody could participate. Maybe using YouTube or something like that, and so or enhance our capacity. So sorry for that. And basically, I would like to, on behalf of the committee, I would like to thank all the participants for actively engaging in the discussion and the session. Thank you very much. Have a good night.
And
Nice.
yeah, I just to to thank you, Engineer. Thank you, Engineer Nandana, President, as well. Just thank you for your very kind comment about my presentation as well. Thank you.